Hello students, in last lecture we have discussed the topic that is second order reaction. In that we have discussed the two different cases. First, second order reaction with equal initial concentration and its derivation. Second, second order reaction with unequal initial concentration and its derivation. After that, we have discussed the characteristics of second order reaction. In that, we have discussed the nature of graph for equal and unequal initial concentration. Similarly, half-life period for equal and unequal initial concentration. And finally, unit of second order reaction. At the same time, we have discussed the comparison of rate laws for zero, first and second order reaction. Now, in today's lecture, we are going to discuss the next topic, that is third order reaction. Third order reaction are of rare occurrence. In third order reaction, the rate is directly proportional to the third power of concentration of reacting substance at constant temperature. The example of third order reactions are the reaction of nitric oxide with O2, that is twice NO plus O2 gives twice NO2, or the reaction of nitric oxide with chlorine, that is twice NO plus Cl2 gives twice NoCl, or the reaction of nitric oxide with bromine, that is twice NO plus Br2 gives twice NoBr, or the reaction of nitric oxide with hydrogen, that is twice NO plus H2 gives N2O plus H2O. These are some examples of third order reaction in gaseous state. Now, derivation of rate law. Consider the general reaction A plus B plus C gives product, or 3A gives product. Now, the rate of this reaction is written as rate is equal to K3 into concentration of A into concentration of B into concentration of C, or rate is equal to K3 into concentration of A cube. It is equation number 1, where K3 is known as rate constant. Now, we will consider a case where the initial concentration of all the reactants are equal, and hence the above equation 1 can be written as rate is equal to minus d into concentration of A upon dt is equal to K3 into concentration of A cube. It is equation number 2. Now, integrated rate law for third order reaction with equal initial concentration can be obtained by separating the variables and integrating equation 2 between the limits of t is equal to 0 to t is equal to t, and concentration of A is equal to concentration of A0 to concentration of A is equal to concentration of AT. We get integration of minus d into concentration of A upon A cube, limits from concentration of A0 to concentration of A is equal to integration of K3 into dt, limits from 0 to t. The integration of 1 upon A cube is 1 upon 2A square, and integration of dt is t. Therefore, by substituting the value of integration and applying the limits, we get 1/2 into bracket 1 upon a square into limits from a0 to a is equal to k3 into t limits from 0 to t. By applying upper and lower limits, we can write the equation as 1 half into 1 upon concentration of a square minus 1 upon concentration of a0 square is equal to k3 into t. Now the expression for third order rate constant k3 can be written as k3 is equal to 1 upon 2t into bracket 1 upon concentration of a square minus 1 upon concentration of a0 square. It is equation number 3. Now the more useful form of equation 3 can be obtained as follows. Let small a be the initial concentration of the reactant A and X be the concentration of the product, and A minus X be the concentration of unreacted reactant at time t. Therefore, concentration of A0 is equal to small a and concentration of A is equal to A minus X. By substituting these values in equation 3, we get K3 is equal to 1 upon 2t into bracket 1 upon A minus X square minus 1 upon A square. It is equation number 4. Now, the above equation 4 can be simplified as K3 is equal to 1 upon 2t into bracket A square minus into bracket A square minus twice AX plus X square bracket complete divided by A square upon A minus X square. The term in the bracket A square minus twice ax plus x square is the expansion of the term a minus x bracket square. Now, by removing the bracket, we can write the equation as k3 is equal to 1 upon 2t into bracket a square minus a square plus twice ax minus x square divided by a square into bracket a minus x square. The common terms a square get cancelled and 2ax minus x square is remained in the numerator. By keeping the x constant, we can write that equation as x into bracket 2a minus x, and by taking the a square from the denominator outside the bracket, we can write the final equation for k3 as 1 upon 2t into a square into bracket x into 2a minus x divided by a minus x square. It is equation number 5. This equation is known as integrated rate equation for third order reaction with equal initial concentration. Now, the characteristics of third order reaction. All the third order reaction satisfy the following rate equation, that is K3 is equal to 1 upon 2t into a square into bracket x into bracket 2a minus x divided by a minus x bracket square. Now second graphical representation. The above equation 4, that is K3 is equal to 1 upon 2t into bracket 1 upon a minus x square minus 1 upon a square can be rearranged and written as 1 upon a minus x bracket square is equal to twice k3t plus 1 upon a square. By plotting the graph of 1 upon a minus x bracket square against time, the nature of the graph is straight line, having the slope twice k3 and intercept on the y-axis is 1 upon a square. Third one, half-life period. It is defined as the time needed to react half of the initial concentration of the reactant. It is denoted by T half. When T is equal to T half, the reaction is half completed. At T is equal to T half, X is equal to A by 2. Obviously, A minus X is also equal to A by 2. By substituting these values in the above equation 5, that is K3 is equal to 1 upon 2a square T into X into bracket 2a minus X upon a minus X square, we get K3 is equal to 1 upon 2a square T half into bracket a by 2 into bracket 2a minus a by 2 divided by a by 2 bracket square. Now by multiplying a by 2 into 2a and a by 2 into a by 2, we get a by 2 into 2a becomes twice a square upon 2 and a by 2 into a by 2 becomes a square upon 4. By taking the LCM of this quantity, we get 3a square divided by 4. Now the quantity from denominator, that is a square upon 4, you have to take it to the numerator, then it becomes 4 upon a square. Then the common terms a square and the 4 get cancelled and 3 is remain in the bracket. Therefore, K3 is equal to 3 by 2 a square T half. Therefore, T half is equal to 3 divided by 2a square K3. At a given temperature, K3 is constant for a particular reaction. Hence, T half is directly proportional to 1 upon a square. Hence, the above equation shows that half-life period of a third order reaction is inversely proportional to the square of initial concentration of the reactant. Now, units of rate constant K3. K3 is equal to 1 upon 2t into a square into bracket x into 2a minus x divided by a minus x square. In this equation, the concentration terms x, 2a minus x and a minus x square are cancelled and another concentration terms a square along with time appears in the denominator. If the concentration is expressed in moles per liter and time in second, then the units of K3, that is rate constant, will be liter square per mole square per second. With this brief discussion about the third order reaction, we will stop here and see you in the next lecture. Thank you.